Okay, so now we're going to have the examples doing some of the integral tests. We've already done one example here. Let's start with another easy example here, just to make sure we understand how we can apply this here. So we're going to start with an example, and let's just look at the series from k equals 1 to infinity of 3 over k to the 4th power. Okay, so this one, again, when it's an integral test, sorry about that, just drinking some more coffee. When we're doing an integral test here, we have to set up my integral, so I'm going to just look at integral from 1 to infinity of 3 over k to the 4th not 3 over k, I like to do these as x, it says it doesn't really matter, dx, which is going to be equal to the limit as b goes to infinity of the integral from 1 to infinity of 3x to the minus 4 dx, which is equal to, well, this would be the limit as b goes to infinity, and if I add 1, that would be 3, so this would be negative x to the negative 3 from 1 to infinity. Not 1 to infinity. I'm messing up here. These shouldn't be infinities. I need you guys to keep me on track here. 1 to b. Alright, so we got integral from 1 to b. 3x and negative 4. Integrating that, we add 1, so we get a negative 3. Divide by the negative 3, so we get 3 divided by negative 3, which is negative 1. X to negative 3 from 1 to b. Alright, so then this is equal to the limit as b goes to infinity of, I'll go ahead and convert it back here, negative 1 over x cubed from 1 to b. Kind of belaboring this a tiny bit here. Negative 1 over b cubed, and this would be, because it's minus, so it'd be a plus because it's minus a negative, 1 over 1 cubed, which of course, as we go off to infinity, this goes to 0. So this is just equal to 1. So the integral converges. So the series from k equals 1 to infinity of 3 over k to the 4th converges. Now that is all you can say here. I want to emphasize this here. You might not even want to put it in your notes. I see people doing this and it's 100% wrong, and you will lose a significant amount of points if you do this. You cannot, I'm going to underline it a whole bunch of times here, cannot say that this series of 3 over k to the 4th converges to 1. You absolutely cannot say that. That is not what the integral test tells us. It only tells us whether something converges or diverges. And if we think about this for a second, it shouldn't take us too long to convince ourselves that this doesn't even make sense, because just write some terms down here. So you have the sum from k equals 1 to infinity of 3 over k to the 4th, which if you were to write this out, this would be 3 over 1 to the 4th plus 3 over 2 to the 4th plus 3 over 3 to the 4th, so on and so on. but this is going to be 3 plus 3 over 16 plus 3 over 81, so on and so on. Well, it's already bigger than 1, so how could it possibly converge to 1? So the integral test does not tell us at all what the series converges to. It only tells us if the series converges or diverges. That's very important. Remember, there's only 2 special cases with series that we get to determine whether the series, what it converges to. That's the geometric series and the telescoping series, which you talked about in section 8.3. The rest of the stuff we're talking about in this chapter is just tests to determine whether it converges or diverges. All right, so let's look at another example here. Okay, so let's look at the series here from k equals 1 to infinity of k over the square root of k squared plus 4. So we know this is going to be an integral test because it's in the integral problems. We'll talk as we start getting into more tests how we can determine it. How I know this isn't divergence theorem is you can do a quick limit in your head here and you see it's going to go to 0. The terms are going to go to 0. But also you want to kind of look at it as like, well, is this something I could integrate? And we want to be careful and not get ourselves going down the wrong track here. We're not going to have to do any kind of super fancy integration techniques in this chapter. I will tell you that the integration problems here will either be just a straight U substitution or integration by parts. There's not going to be any kind of weird, trig substitutions or things like that. So let's look at the integral here. So it's the integral from 1 to infinity of x, and I'm going to go ahead and write this as x squared plus 4 to the negative 1/2 dx, which is going to be the limit as b goes to infinity of the integral from 1 to b of x times x squared plus 4 to the negative 1/2 dx. Now this I'm going to have to do a u substitution on it, so we'll let u equal x squared plus 4. du would be then 2x dx. So I'd have 1/2 du is equal to x dx. And then changing my bounds, if x is equal to 1, u is equal to 5, if limit as b goes to infinity of x equals b, then this would still be the limit as b goes to infinity of u. Because, I'm still going to infinity, so I can just quickly, just say this of b here, of u equals b. Desktop. U equals b. So I can still just write this here, that this would be then the limit as b goes to infinity of the integral from 5 to b, and then this would be 1/2 u to the negative 1/2 du, which would be the limit as b goes to infinity of u to the 1/2 evaluated from 5 to b. So this would be the limit as b goes to infinity of b to the 1/2 power minus 5 to the 1/2 power. Now, of course, 5 to the 1/2 power is just the square root of 5, but we have to think of what happens to the square root of b as you go off to infinity. And again, we shouldn't be too surprised by this. We should be accustomed to things like this. This goes to infinity. So the integral diverges to infinity. So what's our conclusion then? Our conclusion is that the series diverges. Now, I wouldn't say a series diverges to infinity, although that is probably what it goes to. We just really are interested in the fact that the series diverges. Okay, we got one more example that I want to do. Alright, so the other example I want to do here is series from k equals 1 to infinity of k over e to the k. Now there's actually other ways we can approach this particular series, which we'll see in other sections, but this one again would go to the integral test. Now let's just remind ourselves though, if you look at here, we're going to do integral test, but let's just remind ourselves here, because I want to be able to compute these limits efficiently. This is going to equal 0. We know that's going to equal to 0 because e to the k outstrips any polynomial. Remember when we talked about growth rates? Growth rate of e to the k is much bigger than k. So that's going to outstrip it. So that's just going to equal 0. And then what else do we have here? Well, we need to set up my integral then. So I have to integrate from 1 to infinity of x over e to the x. dx. So this is going to be the limit as b goes to infinity of the integral from 1 to b. Now what I'm going to do here is I'm going to write this as x times e to the negative x dx. Now we have to integrate this, and this is again where we have to use integration techniques. And if we look at this for a few seconds, hopefully you can all see what the technique is that we need to use. The technique that we need to use here is integration by parts. And so you'd let u equal x, du equals dx, dv would be e to the negative x, and then v would be negative e to the negative x. And so we'd get that this is then equal to the limit as b goes to infinity of u times v, so it'd be negative x e to the negative x. And this is going to be evaluated from 1 to b, minus the integral of v du, which would be negative e to the negative x dx from 1 to b. So this would be limit as b goes to infinity of negative x e to the negative x from 1 to b plus the integral from 1 to b e to the negative x dx. Then what we do here is we just finish off this integral. So this would be the limit as b goes to infinity, and I'm just going to write this as one long substitution that I'm going to have to do. Because I'd get x minus e to the negative x minus e to the negative x. Alright, so then if we evaluate this, this would be the limit as b goes to infinity of negative b e to the negative b minus e to the negative b minus negative 1 e to the negative 1 minus e to the negative 1. Now, we have to evaluate a limit here. This limit here is easy. We should know that negative exponentials go to 0 as you go off to infinity. Now this again is where you want to use growth rates, or you have to use L'Hopital's rule. But growth rates, we know that exponentials always beat polynomials. So the polynomial is going off to infinity, but the exponential is going to 0. So the exponential we know wins. So this also goes to 0. So this is equal to e to the negative 1, which if you wanted to write it, it's 2 over e, but that's just some number. I don't know what it is. You could divide it. It's a little less than 1. But what we have here is then that the integral converges. So the series converges. So again, what we're basically stating is that if we look at this series of k over e to the k converges. Again, note that I'm just saying it converges. I'm not saying anything about what it converges to. Okay, so to wrap up where we're at here, just to remind you of what's going to be happening here, is on 8/29 on Monday, this is going to be go over homework from 8/1 to 8/4. I will try to get solutions posted. I don't know if I will be able to. I think I'm having an MRI today. It might be tomorrow though, so it just depends on when I get back into Fort Wayne. So, but Monday we will have regularly scheduled class, and we'll go over homework from 8/1 to 8/4. If we don't have enough questions, then we will continue on, time providing, to 8.5. Obviously, if time allows for us to do that. I will give us most of the class period or all the class period if necessary to go over the homework, since we haven't been able to effectively go over the homework online here. And then reminder also that 8/31, which is Halloween of course, we have a quiz, and this is going to be on 8.2 to 8.4. Alright, so hopefully you guys have had a good week still. Hopefully you're watching the videos, and I will see you, I might see you, some of you tomorrow, but I for sure will see you all on Monday.